Hi, we're Group 5, and for our final data science project this semester, we analyzed flight data to predict flight prices.
So getting from place to place is a regular routine in our daily lives, and flying is no different. There are many factors that could potentially affect plane ticket pricing. We wanted to explore US flight data and figure out which factors had the biggest influence on these prices. And we think it's a significant problem because for those who have flown on a plane, we don't have as much of an idea of what goes into this pricing, although one would assume that distance would play a decent role. So we formulated some questions and had some hypotheses based on those. And we hypothesized that distance traveled would be the strongest correlation with flight price, and that the ridge regression model would potentially be the most accurate machine learning model. And you'll see what the results of those hypotheses were when we went more in depth. We got our data set from Kaggle, and it was posted by user Ryan Zernak. And he also got that from the Bureau of Transportation Statistics that releases this flight data every year. It originally had 9 million rows of data with 13 column features, but we were able to extract a sample from that for analysis. The data had multiple feature variables like origin, destination, and miles, just to name a few. And we had an outcome variable, which in our case was price per ticket.
Okay, in our data wrangling, we decided to drop 4 columns, 2 of which were unnamed, and the other 2 being origin WAC and destination WAC. These 2 columns were deemed redundant because we had columns for origin destination airports, and so we didn't need the destination origin WAC codes. And the airline company column in our data had 2-letter codes representing each airline. We used the replace method in a dictionary to change all the coded values to their full airline title to be better understood in our visualizations. In addition, the full 100,000 rows that we had from GitHub was used for the visualizations, but a smaller subset of 10,000 was set aside for use to train our regression models. Our first visualization is a plot-leak disk plot consisting of a histogram and a curve representing the frequency of ticket prices as a percent density of all tickets. The x-axis represents the price per ticket, with the y representing the frequency. The curve illustrates a positively skewed distribution as the frequency peaks on the left and decreases on the right. The most common ticket price ranges from about $140 to $160 US. The second visualization is a bar graph showing the number of flights sorted by airline company. The x-axis shows the airline, and the y-axis is the number of flights attributed to that airline of the 100,000 row data set. Southwest Airlines had the most flights in this data set with 24.5 thousand flights. We had hypothesized that distance travel would be one of the best indicators of price per ticket. To visualize this relationship before training the model, a scatter plot was created with a box plot at the top. The scatter plot and trend line indicate a positive correlation between miles traveled and the ticket price for a flight. This relationship will be explored more later with regards to importance in our model. The box plot at the top helps to characterize the distribution of the miles traveled data as well.
Once we had our cleaned data set, it was time for us to apply the 5 different models that we were going to apply and test for our data set. These 5 were linear regression, ridge, lasso, k-neighbors regressor, and linear SRV. We ran into an issue where we were having trouble applying the models for both categorical and numerical feature columns. And what we ended up doing was applying one-hot encoding to categorical columns and scaling to numerical columns through a pipeline. Once we had that pipeline, we then applied select k-best to our 5 regressors and was able to find the best k value for each model. Once we had that k value for each model, we applied R-squared and mean squared error to all 5 models to determine that ridge had the best reliability in comparison to the rest of the models, and decided to continue down the line with hyperparameterizing tuning ridge as our model. And once we had that model, we applied our feature importance to it and found that the origin was the most influential feature in determining a ticket price, which went against our hypothesis that it was going to be distance traveled. For the finality of our performance of a model, we tuned ridge to find that the optimal alpha value for that model would be 10. And once we had that value of 10 and our k value, we applied the test set to ridge and found that our R-squared and root mean squared error indicated that our data wasn't well suited for ridge regression, because especially with the R squared value, you can see that our model would not very accurately depict or guess the target value, as in our flight price tickets.
So in conclusion, we were able to compare these 5 regression algorithms and found that ridge regression yielded the best R squared value, but even this selection wasn't a good fit for our data. Given our results, we could deduce that ticket pricing can depend on a variety of variables. Our hypothesis that ridge regression would yield the best outcomes was true, so we'll accept that, but miles traveled being an important feature turned out to be false, so we'll reject that hypothesis. To expand on the scope of our project, we could have used a much larger sample or considered multiple years and maybe new types of variables. However, we could say that our process was in depth and could be replicated by other data scientists. And that's our project. Thank you.
Thank you.